you learned from the last lecture? What did we talk about last time?
First generation and next generation sequencing.
Say that again?
Sequencing.
Yeah, sequencing. We talk about 3 types of sequencing technology. What is the first generation sequencing technology?
Sanger sequence.
Sanger sequencing. What is the major feature of a Sanger sequencing? Really effective? Yes, it's highly accurate. It's the gold standard out there, the sequencing. Anything you want to add about Sanger sequencing?
It uses DNTP and DNTP.
Yes.
To
What's special about DNTP?
they will stop transcriptions. They will they'll end the sequence so you can know what based on that.
Exactly. So DNTP is a terminator of the synthesis. So once it's incorporated, the synthesis will stop. So the fragment will be at a fixed length. So once you run the gel, you can determine at a specific length, you have that specific nucleotide because each DNTP is labeled by fluorescence. What about second generation sequencing technology? What is special about second generation sequencing technology?
They can simultaneously do multiple sequences.
Yes, high throughput, highly parallelized. And what are the 2 major companies that produce device based on second generation sequencing technology?
Illumina and Roche or 454.
Yes. What is the approach used by Illumina to amplify the DNA template? Say that again? Rich PCR. What about the alternative in 454? What kind of PCR was that in 454? Emulsion. Yes. And what is sequencing by synthesis? Is Sanger sequencing one type of sequencing by synthesis?
Yeah.
Yes, it is. Sequencing by synthesis is any type of sequencing that involves polymerase. So you use template, use a polymerase to synthesize the complementary plane, and in that process, which nucleotide is incorporated. It is in comparison to sequencing by ligation, but sequencing by ligation is not really important. We are not going to have that in the exam. And we talk about sequencing by synthesis mainly because it was the major technology used in the Illumina Solexa sequencing. And in Illumina Solexa sequencing, they use a special kind of reversible terminator. So once that terminator is incorporated, the reaction will stop. So you can read which nucleotide is incorporated. And then you can reverse, you can kind of remove one blocking group in the molecule so that you can continue to add a new nucleotide. And that is the key feature for the Illumina Solexa sequencing. And last question, third generation sequencing technology. What are the 2 companies that have third generation sequencing technology? Or the 2 type of third generation sequencing technology? Any? PacBio is one. What about the other one?
Oxford Technologies with Nanopore.
Yes, exactly. You can just say Nanopore. So those are 2 major companies that are doing third generation sequencing technology. What is the one key feature for the third generation sequencing?
There's no amplification for it.
Yes, no amplification. So if you provide one DNA, it will just sequence that DNA. It's called single molecule sequencing. Cool. So those are the kind of questions that is going to be in the quiz and exam. Hopefully that's not that difficult. Okay.
Like on Tuesday.
After the exam, let me know what you think about the exam. If it's too difficult, let me know. I am not going to have any trick questions. I don't know how to make trick questions. So give me some feedback after the quiz so I can adjust later. Today we are going to talk about mutation. So mutation is kind of significant in genetics because mutation is the ultimate source that causes all the genetic disease, heritable disease. Mutation is also the ultimate source of genetic variation. So in 2 lectures ago, we talked about human genetic variation. Where did those human genetic variation come from? Ultimately, they come from mutation. And mutation is also the raw material for natural selection to happen because natural selection acts on specific mutation. If that mutation is deleterious, it will be removed by natural selection. If it is adapted to a specific environment, that mutation will increase in frequency. That's called positive natural selection. So I think this summary of natural selection is very accurate. So mutation propose different kind of possibility, and then selection select from those possibilities. And mutation is kind of a molecular clock. You can think about the happening of mutation is kind of random. So it's like the molecular clock. So we can use when you compare 2 sequences, by looking at how many difference between those 2 sequences, we can kind of estimate what's the time between those 2 sequences. For example, if we get a sequence from human and compare that sequence to chimpanzee and count the number of difference between those 2 sequences and assume that the mutation rate is constant between human and chimpanzee, then we can the difference divide by the rate, and that's the mutation rate, will give us an estimate of when human separate from chimpanzee. So mutation rate is widely used in evolutionary analysis as a molecular clock. There is some problem with it. We are going to mention, not going into detail here. Germline mutation and somatic mutation, just as the name suggested, germline mutation are mutations that happen in the germline. Somatic mutations are those that happen in the somatic tissues. And germline mutations are the mutations that are transmitted from one generation to the second generation. Somatic mutation could not be transmitted, but somatic mutation is still important because they can cause cancer. Because, for example, if some mutation cause the uncontrolled growth of some cells that can develop into cancer. And the type of mutation are similar, but the mechanisms that trigger germline mutation and somatic mutation could be different, and so they can have different patterns of mutation. But for today, we are mainly going to focus on germline mutation. In terms of types of mutation, this is actually the same as the types of genetic variation we already talked about in 2 lectures ago, so this is easy. The first type is point mutation, the mutation that create single nucleotide variant or single nucleotide polymorphism. The other type is the insertion deletion mutation that resulted in indel. And the larger one, structural variation. We already talked about this. In terms of mechanism and how the mutation happen, so there are 2 major sources. The first group of the first major category is errors associated with replication. So the replication of DNA. So, for example, in this process, this is the template, and we are trying to synthesize the complementary strand. In that process, there could be a slippage in the template. For example, in this case, there's a loop out of the newly synthesized strand. So the newly synthesized strand has an insertion of A. In this case, if the template strand loops out, it creates a deletion in the new strand. So this kind of X instance is called strand slippage during DNA replication, and this kind of strand slippage can introduce insertion deletion in DNA strand. The other type of error during replication is simply the misincorporation of nucleotide. Because we know that nucleotide base pairs based on the Watson-Crick principle. So A pair with T, G pair with C. But sometimes, so those are the structure of A, T, G, C. And you can, and sometimes these are the common form. And they can sometimes transform into this kind of rare form. Once they go into the rare form, they can induce base pairing, incorrect base pairing. So those are A and T, G and C. Those is the common form and correct form of base pairing. Sometimes C can pair with A and T can pair with G. And in this kind of misincorporation, it induces point mutation. And you don't need to remember the molecular structure. That's not important. Just remember that misincorporation happens during replication, and that introduces point mutation.
Is one of those two more common than the other?
The misincorporation is more common, and that's based on, if we look at the mutation observed in real data, point mutation is more common. And so this kind of misincorporation happens when the pool of nucleotides is running out. For example, if we have DNA replication at the very beginning, we have sufficient supply of free nucleotides. So you always have the right nucleotide to pair with the template. But later, in replication, you run out of a specific kind of nucleotide. For example, if you run out of T, then in this case, C is more likely to come in place of T, and that can increase the amount of misincorporation. So for when you look at the genome, some part of the genome is replicated early, some part of the genome is later in replication. So the genome that replicated later usually has a higher mutation rate. And this is just an indication, a result from a research showing that regions that has late replication timing tend to have a higher mutation rate. So those three columns represent different kind of site. Question?
Is the depletion of nucleotides associated with a certain disease, or is that just common in everyone?
It's common.
Okay.
So this kind of feature, more mutation in late replicating region, this is a common feature across everyone. And actually, there's some study that some kind of dietary deficiency resulting in insufficient supply of nucleotide, and that can actually increase the amount of DNA mutation. But that's common across all individuals. So those three columns just represent different kinds of genomic site. This is all genomic site, and these are the CpG site and non-CpG site just separate genomes into two categories. We're going to talk about CpG site in the next slide. But the y-axis, so the x-axis represent replication timing, early replication and late replication on the right. And the y-axis represent is a proxy of mutation rate. What it does here is to use the difference between human and chimpanzee, human and macaque, human and basic monkey, and then different humans. Look at difference across different human or different species, and see how many differences you can observe in different genomic regions with different replication timing. And the pattern is the same. In regions that tend to have late replication, they have a much bigger difference, basically indicating much higher mutation rate. And so I talk about errors associated with replication. The other category of error is not associated with replication. It's called non-replicated error, or sometimes called spontaneous error, because the structure of DNA is not stable. Any kind of chemical structure is not 100% stable. Sometimes it can undergo some chemical structure change and then change the nucleotide. For example, cytosine can undergo spontaneous deamination and transform into uracil. So you have a C change to U, and during DNA synthesis, U will pair with T. So eventually, at that position, CG changed into AT. So this kind of spontaneous deamination can result in change of C to T. Similarly, if the cytosine has a methylation, so this is a methylated cytosine, if it undergo deamination, it goes into thymine directly. So these two kinds of deamination is actually quite common in the genome. And in the genome, we define a group of site as CPG site. Basically, it is two nucleotides that have C and G. And in some region, this kind of CG site is very common. Those genomic region is called CPG island. And the cytosine C in those CPG island is usually methylated. About 70 to 80% of those C in CPG island are methylated. So it created a lot of opportunity for deamination to happen. And that's why CPG site has a higher mutation rate compared to other places. CPG site, when we look at the genome, if the composition of nucleotide is random, like at any position, it could be ATCG. If it's random, we expect that CG, that kind of combination, is going to happen about 4%, a specific percentage. But that's the expectation. But if we look at the real genome sequence, CPG size is actually less than expected. And it's actually accounting less than 2% of the genome. But it accounts for 20% of new mutation we observe. And the underrepresentation of CPG site in the genome is that they have a higher mutation rate. So if you have a CPG site, it has a C mutated to T. So that's why CPG site is less and less.
Wait, so is it, just to make sure, so like, is it because of the CPG islands that causes the deamination, or is it like a mixture of other situations that causes that?
So CPG island by itself is not going to cause deamination. So deamination is sometimes it's spontaneous happen because the chemical structure is unstable. Sometimes it can be triggered by other factors, but it's not the CPG sequence by itself.
So it accounts for less than 2% of the sites, but in in a baby or someone, are the CPG islands, or like is there more CPG islands than there are, or like more CG pairs than there are in adults?
So again, yeah, I would say
Like, are the mutations happening throughout our life and like it was more than 2% at one point and now it's 2% like as adults, or is it just like over time through evolution, like it's just gone lower and lower?
so you are saying that is the percentage of CG site increase over time
Mm-hmm.
by generation to generation, and the answer is yes, and that's why CG site are less than expected, but it's not going to zero. Yeah. Any other questions? So here I just want to introduce the concept about transition and transversion. So when you look at the chemical structure of ACGT, so usually they are classified into two groups. C and T are pyrimidions, so they share similar chemical structure. They have only one ring. And A and G has two rings, so they are called purines. So if the change happen between the nucleotides that has similar structure, either between pyrimidion or between purine, it's called transition. And if it happen from two ring to one ring or from one ring to two ring, it's called transversion. And there are only two possible types of transition, but there are four possible types of transversion. So assume that if this kind of change happen at equal rate, then we expect that transversion happen at least 2 times more often than the transversion. But in reality, transition is the one that is more common, because the transition is change between nucleotides with similar chemical structure. It's just easier to happen. And that's why the deamination of cytosine to thymine is so common. The other concept is about strong and weak base pair. The GC base pair has 3 hydrogen bond, so that it is stronger, it's harder to break them apart. The A and T has only 2 hydrogen bond, so they're called weak base pairs. And it has been observed that the mutation from CG pair to AT pair is more common than the other way around. And one of the reason is that higher mutation rate at CPG site, C, change to T. So that's one explanation. The other explanation is that for regions that has high GC content, once you have a mutation, the repair efficiency is lower. But actually, even accounting those 2 factors, we still could not fully explain why the mutation goes in strong base pair to the weak base pairs. So there's still some other factors we don't know at the moment. But this is the observation we have right now. Okay, so we talk about different types of non-replicated error introduced by the spontaneous change in the DNA structure. And then there's another, so those are the spontaneous change. There could be also other changes that are induced by endogenous or exogenous source, basically some, for example, carcinogens, chemicals that induce cancers, and they act by induced mutation in the DNA. And so those are the external factors. There are also endogenous factors in our body that can also induce mutation. For example, so a large amount of oxidative stress in the body can also introduce mutation. So different kind of factors can trigger mutation, but the type of mutation they trigger are different. For example, for UV light can induce mutation, but the kind of mutation they induce are usually C to T or CC to TT mutation. And that's why this kind of mutation pattern is usually found in skin cancer patients. Another example is for smoking. Smoking can introduce G to T transversion, and this kind of mutation is frequently observed in lung cancers. So sometimes when we, for example, if we get samples from different kind of patient and you look at their mutation signatures, we can kind of infer what was the major environmental factors that trigger that kind of mutation. So we talk about two major categories of errors. The things that once those errors are introduced in our DNA, there are still ways to repair those errors. So actually our DNA system has multiple repair systems. So they're actually quite efficient at repairing those errors. If those errors are repaired, then there is no mutation. But if those mutations are not if those errors were not repaired, then they become mutation. So the number of mutation is really determined by the error rate and the efficiency of DNA repair. So we talk about different types of mutation, and now I'll talk about how do we study human mutation. And one way to study is to look at genetic variation, because genetic variation comes from mutation. So that's what we can do when we compare different individuals and look at the difference. We can also compare different species. Here I list 5 approaches to study human mutation and also to infer the rate of human mutation. Let's go through them one by one. The first approach is based on a certain type of disease, genetic disease. For example, if a specific mutation can cause a severe disease, so that kind of disease, so that mutation has to be dominant in compared to recessive. For recessive genetic disease, you need 2 copies of mutation in order to have to show the symptom. So for this kind of mutation, we can count. For example, we can count the prevalence of that specific genetic disease in the general population, and that can give us an idea of how often that mutation happens and help us estimate the mutation rate. The problem with this approach is that, as I mentioned, you can only use disease that are highly penetrant. Is that once a person carries a mutation, he will have the symptom. And still, that mutation could not cause death before the child was born. Otherwise, you won't be able to observe the patient. So, and also, you only look at loci that are associated with disease. So the number of loci you can use is actually kind of small, and that kind of loci may not be representative of the whole genome. And this is the limitation of this approach. The other approach is called pedigree-based approach. You collect data from each family, and this is called a trio design. Basically, you have 2 parents and then 1 child. It's called trio. And then you can look at mutations that is only observed in the child, but not in the 2 parents. And the problem the benefit of this design is that you look at, now we have genome-wide sequencing, you can sequence the whole genome. You can directly observe mutation. And the problem is that mutation rate is low. Usually, in each generation, there are less than 100 mutations. So it's a small number compared to the size of the genome. And when you do sequencing, there are always errors in your sequencing technology. How do you differentiate sequencing error and a new mutation? And that's always challenging. So usually you need to have a large number of categories to average out error so they can get a relatively accurate estimation of mutation rate. But this kind of design is only available recently because we have whole genome sequencing. The other design is still based. It's not really pedigree. It's actually you use genome from individuals that are relatively close. You focus on, so for example, those are these two parents give rise to these two child, and so the blue chromosome. Look at these two blue chromosomes. We know that they are from the father, and this chromosome has dark blue and then light blue. So it is a result of recombination in the father, and this is also from a recombination in the father. But the thing is that this whole light blue region, they are all from this chromosome. So in this case, the two alleles, so this allele and this allele, descended from a common ancestor not very distant ago. This kind of allele is called autozygous. Basically, it's also called identical by descent. They are identical because they descend from a common ancestor. That's called identical by descent. By comparison, sometimes two sequences could be the same, but it was not because they descend from the same ancestor. It's just because they happen to be the same. That's called identical by state. They are identical, but they are not from the same ancestor. So if we know that these two regions are identical by descent, they're from the same ancestor, if there's no mutation, those two alleles should be 100% the same. And in this case, if we find a difference in those two alleles, then those differences represent mutation happen in one of the germ cells. So that's another way to infer mutation rate. The problem with this approach is that you need to first define autozygous region. Basically, you need to define that this region and this region is autozygous or identical by descent. And defining that boundary is always challenging, and that's one limitation. And so all these approach, the first three approaches I mentioned, is all kind of pedigree based. The other two approach I want to mention is phylogenetic based, by comparing across species or subspecies. It's also called comparative genomics approach. The first approach is that we compare the genome of different primate species, including the human, and we count the difference across different comparisons, and assume that we know the time when the two lineages separated. So the difference divided by the time will give us an estimate of mutation rate. So that's the first approach. The second approach is that assume that we have some ancient DNA, could be, for example, the Neanderthal. It could be some modern human from, for example, 10,000 years ago. So basically, those DNA comes from 10,000 years ago. So they, compared to the present day individuals, their mutation stop here. They no longer have new mutation introduced to the DNA. So we can count the difference, how many of the mutations we expect to see but we didn't observe. Those mutations represent the mutations that can happen in this specific time frame. So that's another approach to estimate mutation rate. The problem with this kind of phylogenetic approach is that you need to make some assumption, especially how much time happened when the two lineages separated, or how much time is the age of that ancient human DNA. And all those estimates could be inaccurate. So based on all those different kinds of approach, right now, so those are different studies. So different x-axis represent estimate from different study, and different study use different approach. The y-axis is the mutation rate, human germline mutation rate. You can see that from different study, there is actually some difference. There's some inconsistency based on the different study, and actually there's actually still no consensus about why some studies are different. And one major inconsistency is between the pedigree data approach and the phylogenetic approach. The data is based on looking at trio data, trio design, or data is looking at comparing human to other species. That two major approach has a major inconsistency in their estimate of mutation rate. But overall, in terms of scale, the consensus right now is that if you look at mutation rate per base pair per year, it is about 0.5 by 10 to the negative 9. If you look at mutation rate per generation, it is about 1.5 by 10 to the negative 8. And you need to remember those two scales. It's about, if you talk about per generation, mutation rate is about 10 to the negative 8. And in order to make the conversion between these two kinds of mutation rate, you need to have information about how many generations we have per generation, how many years we have per generation. And here the assumption is about 30 years. And that generation time can differ in different human population and in different historical periods. Before I move on to the paper aside, I want to give you a break. 5 minutes. Shows the relationship between different species. And the way we build this kind of tree is based on, for example, there are different ways to build phylogenetic tree. You can use like anatomical structures, like basically human and chimpanzee share more common features in anatomy or in physiology. You can use that kind of shape to build this tree. But more recently, we can use DNA sequence to build this tree. Basically, you have a DNA sequence for different species. You compare the difference, the number of difference in each pairwise comparison, and species that are closer to each other share a less number of mutation. Species that are further apart, they have more time for mutation to accumulate. So they are further apart. And for example, also similarly for human and other ancient DNA, you can build this kind of tree based on DNA. So sometimes this kind of tree, when, for example, if you have a new sample from chimpanzee and new sample from human, you don't really need to build this tree again, because this relationship right now is kind of a consensus. No one will really argue about this kind of relationship. So you can use this kind of information in your study. And then about how do researchers get these two numbers? So as I mentioned, different study kind of give a different number. And here the point here is called point estimate in statistical analysis. Basically, you estimate a number for mutation rate. And that, we know that that number is just an estimate. It's not the truth. And so there could be some error associated with the point estimate. And the line here is called the interval estimate. That estimate, basically, if the line is very long, it indicates that there's a lot of uncertainty in this point estimate. But you don't really need to know this. The point in this slide is I want you to know the scale of the mutation rate, because it's 10 to the negative 8 or negative 9. It's not 10 to the negative 2. that will make a huge difference. And this number is kind of like here, so it's kind of like an average over most studies. Okay, we want to go into the paper today, and supposedly the only thing I expect you to do before class is to read the paper. We have two required reading. So one is the perspective or is the news, and that one supposedly is easier to read because it doesn't go into the details of the method. So that one should be an easy read, and then you also need to read the research paper. So assume that you have read those two pieces. Share with me one or two things you learned from that.
Males should freeze their sperm early.
Good. Great summary. Why? Not for you to answer. Anyone can explain why?
There's an increase of mutation rates per year as the age the man increases, which I thought was interesting because I'd never heard any of that. I had just heard like maternal age and like freezing eggs, and so it's interesting how this paper was like, maybe you should freeze your sperm to do that. So.
Awesome. Anything else you want to share based on reading the two pieces? What about like in a newborn, how many new mutations you can expect to observe? So like 2 lectures ago, we talked about when we sequence a new genome, from any individuals and compare that genome to the human reference genome, how many differences you can observe, right? Does anyone still remember that number, the scale? A few thousand? A few billion? A few million? Like when you compare any two genomes, how many differences you can expect to observe? It's going to be in the quiz or exam. Yeah, it is a relatively important number. Anyone remember that number?
100?
100. So if I compare my genome to your genome, 100 difference?
I thought it was between the parent and the child.
Oh no, I'm talking about 2 lectures ago when we talk about genetic variation.
In comparison to any genomes.
1,000? we have only 1,000 difference.
I thought it was like 9 million or something, but I think that's too much.
So the scale is a few million. Yeah, it's a few million. It's about 4 to 5 million when you compare any two genome. But now we are talking about new mutation. So the genetic variation when you compare two genomes is mutation that accumulated over many generations of mutation. Now we're talking about in a child, this child inherits some mutations that happen in their parents. This 1 generation ago. New mutation that arise in 1 generation. So how many new mutations we expect to observe in a child? You mentioned 100. It's actually right. It's about 100. Based on this paper, it's actually about 60. Okay. So this paper was actually not that new. It's 2012, and 2012. Remember that next generation sequencing, the 2nd generation sequencing technology was really mature in about 2008, and it was gradually developed to sequence more and more stuff, sequence any kind of stuff, and sequence whole genome. So in 2012, considering that in this study, they sequenced a large number of individuals, they actually sequenced a few thousand individuals. It's whole genome sequencing. So it's actually kind of early in this kind of study, 2012. And after that, there are many more follow-up studies. And in this study, it mainly focused on the effect of the father's age on mutation. And it seems that based on this study, they didn't observe the maternal age. But later in other studies, they were able to observe similarly as women age. The mutation rate will increase slightly, not as dramatic as the paternal age. And the type of mutation as a female age, the type of mutation is actually different from the type of mutation that are from paternal age. In female age, the type of mutation that become more common is actually large-scale structural variation. But that's not the point of we are going to cover here. In this study, they focus on de novo mutation. De novo mutation basically is just mutation that was observed for the first time in the family. So that's why it's called de novo. It's just new. And we have de novo genome assembly, basically we assemble a new genome. And de novo mutation, one thing to pay attention is that de novo mutation can actually happen in the germline of the parent. So that's germline mutation, but it can also happen in the fertilized egg. So after the egg was fertilized, in the early embryonic development, some mutation can happen. And basically, in the real study, they only look at mutations that is present in the child, but not in the parent. That's how they define de novo mutation. There's a slight difference between germline mutation and de novo mutation, because de novo mutation also include mutations that happen in the early stage of the embryo. But usually, people just equal germline mutation to de novo mutation. And proban, this is a medical term. It's basically, usually in medical research, you start with the patient. We suspect that that patient has some genetic disease. We go back, collect more samples from the family, try to locate the genetic mutation. So the first patient in the family that is under study is called proban. So in this case, it's the child. Question?
So you said there's a difference in opinion on whether a de novo mutation is like in the germ cell of parents or not. For the purposes of your exam, can we consider a mutation in the sperm or egg cell de novo mutation?
Yes.
Okay.
So mutation in the germ cell is 100% de novo mutation. It's just that de novo mutation has another source that's from after the fertilized egg. So the de novo mutation includes germline mutation and then some other mutation in the early embryo development. But for the purpose of this exam, you can equal de novo mutation as germline mutation. And for this study, it study mutation, and the study design is using a pedigree design. So remember the 5 types of research approach to study mutation. And this is just one of them, based on pedigree. And this study used 78 trios, 78 pedigree, not 78 pedigree, 78 trios, because it has different kind of pedigree structure. It only has 57 simple trios. It has some other more complex pedigree structure. For example, this has 2 siblings. So it's actually, if you kind of decompose them into simple trios, this accounts for 2 trios. So you have 2 parents, 1 child, that's 1 trio. 2 parents, another child, that's another trio. So that represents 2 trios. And this, you have only 1 trio. That's it. And for this, you have 1 trio here and then 1 trio here. So that's 2 trio in this structure. You don't really need to know this, but just an idea for you to know where does that 78 comes from. And because for this specific study, the way you identify de novo mutation is by looking at the genome of the child and then compare to the genome of the parent. And so if you're looking at this grandchild, it doesn't really help. So it's not used, that information is no use. Only look at the child and then look at the 2 parents. In addition to the 78 trios, they also have about 2,000 genomes, 2,000 participants that are not in this kind of structure. They serve as a general population sample. The idea is that if a mutation is already observed in the general sample, then that mutation is unlikely to be de novo mutation. If a genetic mutation is already observed in the general population, you can remove them from your analysis. In this way, it actually help you reduce the error, because when you try to identify mutations using sequencing data, there are always errors, and you need to use different approach to help you reduce the error. So the criteria used in this study is that for de novo mutation is that mutation should not be observed in the population sample. So it helps reduce the false positive rate, but it also actually miss some of the recurrent mutation, because it's possible that that mutation happened in the general population and that mutation happened again in this specific trio we studied, and that kind of mutation that happened multiple times is called recurrent mutation, and that kind of recurrent mutation is relatively rare. So by applying this criterion, you don't miss much. And then the de novo mutation is observed as heterozygote in the proband, and that's because, so this is called as a heterozygote because it has, the two alleles are different. And the reason that they remove homozygote is that in order to have homozygote, you need to have a mutation in the father, you need to have a mutation in the mother, and that's recurrent mutation. That's very, very unlikely. If you observe a homozygote, it is very likely to be either sequencing error or it's just mutations that they're just regular genetic variation. And then the mutation should not be observed in the somatic tissues of the parents, because they also have the genome of the parents. And the idea is that this mutation, in the development of their parents, the germline cells separate into somatic tissues, and if the mutation only happens in the germline, then those mutation is not in the somatic tissue of the parent. Those are just the details of how to define de novo mutations. And then in this study, they were able to determine the origin, the parental origin of the chromosome. Basically, you have the genotype, the whole genome genotype of the father and the mother. And remember, in the 2 lectures ago, we talked about defining haplotype or haplotype phasing. Is that when you do sequencing, you get genotype, but you can phase them into 2 haplotypes. Each person has 2 haplotypes. And then you can determine the parental origin of the 2 haplotypes of the tribe. For example, this one, we know for sure it is from the father. The other one is from the mother. And there is a mutation. For this mutation, it happened in the father. So in this way, we can determine the parental origin of a specific mutation. And then so in total, in the 78 trios, they observed about 5,000 mutations. If you take an average, in each trio, they observe about 60 new mutations. So basically, in every newborn in their genome, we expect to find about 60 new mutations. And here we only talk about point mutation, didn't pay attention to insertion deletion or other large-scale structural change. So point mutation in each newborn is about 60. So that number is also kind of informative. You need to keep that in mind. Just the scale, if you answer 100, it's okay. And then one important piece of information is that when we look at the parental origin of those mutations, so here in this table, it only shows the information for 5 trios, because in order to determine the parental origin, you need to determine the haplotype of each parent and then the child. Sometimes that kind of haplotype phasing is challenging, and they will only have information for 5 trios. And based on those 5 trios, if you look at so that's the total number of mutation in that trial. It's at the scale of 50 to 100. Look at where are they from paternally and maternally. The majority of them is of paternal origin. And this is only looking about paternal origin and maternal origin. And then you can look at the age of the father. And each dot represents the number of mutation in a child, and that's the number of de novo mutation in that child. The x-axis represents the age of the father and conception of the child. So, and the line here are just different way of trying to fit some statistical model to the data you observe. Those lines is not really important. You don't need to try to understand what are those models they use. But I just want you to know the trend that there is a very apparent positive association between the age of the father and the number of de novo mutation you are going to observe in the father in the child. And on average, based on different model, for every 1 year increase in the father's age, there is about 2 extra de novo mutation in the child. So for example, if you look at a father that is about 20 years old, because it has 10 years old here, it has only about 25 mutations. Based on this figure, it should be slightly more, but it's around there, about 25 mutation. But for a father that is like 40 years old, it transmits 65 mutations to the tribe. By contrast, if you look at the number of de novo mutation from the mother, it is always about 15. Question?
Why is it only, or like, is it 15 if all the cells are formed at birth already, versus if it's 20, it's just a very marginal increase over 15. If it's a 20-year-old male, it's only marginal increase in mutations compared to like at birth cells in the mother.
So you mean comparing this number to this number?
Yes.
So why in a 20 years old father, the mutation number here is still higher than the mother?
It makes sense that it's higher. It doesn't make sense why it's only very marginally higher.
Oh, you expect this number to be
More higher than it is compared to 15, is what I'm saying.
wait.
Or 15 to be lower.
You mean the difference between this number and this number to be bigger?
Yeah, okay.
And why do you expect it?
Well, because the study found 2 mutations per year.
Okay, 2 mutations per year, and you are thinking about 20 years old, you 2 times 20 give you 40. Are you expecting a 40 here?
Yeah, I guess.
Okay, so higher than this. Okay, cool. And the next slide is going to explain why. And that's because, so actually they go back to the lectures given by Dr. Vidal about the germline cell development. When you look at the male germline, it like the male germline was arrested in mitosis after the child is born, and then it was arrested there without any division until puberty. So it's around the age of 13 or around the age that the puberty begins, and then the male germ cells started to divide again. So if you think about that, the years to accumulate mutation starts puberty. So that's why the number is less than 40. Okay. And for female, the primary oocyte were arrested in the prophase 1 of meiosis. So it only later become active before ovulation. So if you count the number of cell divisions for the male germ cells and the female germ cells, each male germ cell experience about over 400 cell divisions, while the female germ cell only experience about 30. And that large number of difference in cell division is responsible for the much higher number in the de novo mutation, and because in each cell division, you go through DNA nullification, and DNA nullification can introduce error, right? And then here we look at mutations by different types. Remember, we talked about CPG island and non-CPG island, and CPG site tend to have an elevated mutation rate. And here, the CPG site, as you can see, the scale, the order of magnitude is actually much higher than mutation at other sites. And the overall mutation rate estimated in this study is about 1.2 to 10 to the negative 8, and this is per generation. Usually when you talk about per generation mutation rate, it is always at the scale of negative 8. So CPG island has elevated mutation rate. And then you look at the mutation from strong base pair to weak base pair. And that's strong base pair to weak base pair, and then weak base pair to strong base pair. And this one, just compare the ratio of the two. And the ratio is always larger than 1, indicating that the mutation from strong base pair to weak base pair is always larger than the other direction. And there are several explanations for it in the last few slides we mentioned. And then the last slide I want to talk about is this figure in terms of when you look at different chromosomes. So this is the average number of, like, what this figure is trying to look at is that we know that paternal age has an impact on de novo mutation. But if you look at different chromosomes, is that in fact different across different chromosomes? The x-axis is the number of de novo mutation observed in that chromosome. The y-axis is the number of mutation increase per years of the father's age. But the take-home message here is that the longer the chromosome, the more number of de novo mutation you're going to get. The more of the increase because of the paternal age. Basically, the paternal effect of mutation is similar across chromosomes, and that's because it was mainly from replication, and all chromosomes need to go through replication. So the more replication you get, the more mutation you get, and that kind of effect is consistent across chromosomes. And this piece of information is not as important as other information I mentioned, so you don't need to work hard on this one. It's kind of trivial. And in terms of implication, now we know that paternal age has a huge impact on the number of mutations in the next generation, and we also know that this is the father's age at conception across history at different historical period, and there was a decrease in the father's age, and then there's an increase in the father's age. So if we take this into account, in different historical period, the number of de novo mutation introduced into the general human population gene pool is different. So the mutation rate kind of changed in different historical period. And then now that we have a later reproduction age for the father, the later reproduction age can introduce a larger number of mutations, and that could be responsible for some of the disease we are experiencing increased prevalence right now. And that's another implication from this study. We have 2 minutes left, and actually I'm wondering if you have any questions about mutation or specifically about this paper. And any questions? No? So when you go back, when you study for exam, you want to go through the slides and also go through the study guide. Make sure that you understand all of the stuff most of the stuff in the slide, not all of them. For example, this one is not as important as other information, and that's it.
I just set it up on top of the thing, and so it wasn't there when I was packing up. I got here and I opened my bag and I was like, where did it go? I just I don't know how you do this.
I don't.
When I have to stay until 3:30 or whatever on Tuesdays, I'm dying.
No, by the end of my bio class, I'm
And you get to